Welcome to the evening session. The dimming of the lights isn't a sign for you to nod off to sleep at this late hour. Peter, I'm pleased to say, has got his newspaper to keep him amused. So it's a great pleasure to be part of this evening, and I've got to say on behalf of the staff, thank you for showing your interest in the research that's being conducted here by attending. The two BSc students who are doing my project, they get brownie points for being here. But unlike you all, they will be examined on this stuff afterwards. I chose a little left field title for this talk, Biological Noise. What do you think of when you read those two words? Biological noise.
Errors.
Errors. So you don't think of this. Let's listen to some biological noise, shall we? This is my children's primary school. Of course, what I'm really here to talk about within the envelope of biological noise is this: order, quasi-order, and disorder when it comes to photonics, when it comes to light and colour and controlling light and colour. Many of you know, some of you perhaps don't know, that I work in biological appearances, understanding the physics that goes into creating some of the brightest, most conspicuous, or the most inconspicuous biological appearances. And it's trying to understand those systems in a biological context and the mechanisms that create them, and apply them to technology that really drives me personally as a scientist and my team in the basement of the physics building. And I should extend right now, if I forget later, any of you at any time are very welcome to come and just ask questions, talk to the guys, maybe see some of the kits and see some of the samples that we work. So here are three of the samples with which we've done a good bit of work so far. And in fact, they're all representatives of various aspects of order, quasi-order, and disorder. Order is a very important concept in physics, especially in electromagnetism. Of course, it is in solid state as well, when it comes to ordered crystals of atoms and how electrons propagate through those crystals. A lot of that is governed by the same principles which govern the interaction of light with some of these structures as well. So let's have a look at what's in today's presentation, and we're going to have, as I can't resist, talking about morpho. And had I known that it was just upstairs, I would have gone and got a couple of morpho butterflies to show you if you haven't seen one before. But if you haven't seen one, and I've forgotten one here, you're very welcome to knock on my door on the 6th floor. I talk about this stuff all the time, and many of you will have heard these types of ideas and seen these slides many times, not least in the waves course that we share together. But iridescent bacteria are a slightly new aspect of work that only recently has been published and recently I've been able to work. And it's quite an exciting borderline. Depends if you're into bacteria or not. But nonetheless, it's a very interesting area. And this idea of bright whiteness, you can see that this object here, this beetle, is very white. And the sliding scale from order through to disorder leads to a sliding scale in appearance from bright saturated colour to diffuse broadband whiteness. I don't use the word colour when it comes to whiteness, because a white appearance comprises all the single colours, as it were, that we can see. So let's motor on. So if I were a bumblebee, let's say buzzing along here at the front of the desk, I won't make those sounds, but would I be a good-looking bumblebee, an attractive bumblebee? What do you think? You don't need to answer that right now, that's more of a rhetorical, silent question. As a husband, attractive or not, probably not these days, I wander through supermarket aisles looking at the colour and wondering which ones to buy for my many hundreds of children at home. 4 If you don't know me well, I have 4 children. So, you know, these colours that the manufacturers, that Unilever and Procter & Gamble use to cover, with which to sell their products, they are an allure. They are trying to attract me. They think I'm attractive as a pollinating insect, so they try to pull me in. If I was a real bee, the flowers would be doing the same job, rather than a wannabe father figure, as it were. So all of these colours here, what I'm trying to say, they are signals. And they're very important signals. The biology of them has been studied very intensely and is well known. The chemistry is very well known. And indeed the functionality, how do they interact with their pollinator systems, that all has been studied and is an extremely interesting area of science. What I'm more interested in is taking this idea of pigment-based colour. You'll notice, without me telling you again, that I've got very grey hair. What was the name of the pigment that I used to have in my hair? You've got jet black hair. What's the pigment in your hair?
I don't know.
Anyway, melanin. Yeah, absolutely right. So I'm ceasing to produce melanin, and the real test is whether your eyebrows are going grey, and I think mine are just starting to go. So the pigment that we see in those flowers is akin to the pigment I used to have in hair, and it's it's a chemical-based mechanism by which colour is produced. The interaction of the interaction of electrons with energy levels, promotion, demotion, absorption of photons, re-emission of the same or other photons. That leads to pigment-based colour, and it's well known, and it's a molecular, it's a chemistry, as it were. Most of us, certainly the staff here, most of us are physics-based. Some of them are a little bit on the periphery, biophys, medical physics, chemical physics, let's say. What the more purist physicist would be interested in when it comes to appearance and colours is this idea of manipulating light. The jargon, the phrase that I'll introduce here is this idea of a photonic band gap. Let's just revive a couple of physics concepts. The first would be this, and this is a rather esoteric diagram. Let me explain it. Y and X are spatial positions. What I have is a big slab of material. This material could be glass, it could be perspex, it could be a volume of water. And that is the Y direction, that's the X direction. What I'm going to do is I'm going to take some light, and this light has an indeterminate wave vector, which is related to its wavelength and hence its color, and I'm going to send it into this material here. Now what happens? Does it propagate? Does it not propagate? Well, what this diagram shows, and unless you're familiar with them, you might not recognize that what I'm going to show you here is the band diagram associated with that problem I've discussed. I'm going to say, as I vary the wave vector along that axis, how does the propagation relate that wave vector to the frequency of light which propagates? We're already in pretty deep water, even with that 1 minute of explanation. But because there is a single solid line here, which actually extends in a straight direction up there, that is the light line. The equation of that line is, well, maybe you can tell me if I ask you the right question. What's the wave equation? Do I need to go to my register? What's the wave equation? You guys knew you'd pay a price for coming this evening. Olivia, what's the wave equation? In school, I'll tell you this, in school you learnt it as V equals F lambda, right? But more here, we don't tend to talk about V, we talk about C. We don't tend to talk about lambda, we talk about K. And there's an omega in there now. So what's the equation? The wave equation relating C to K to omega. You'll never come to one of these things again, will you? Anyway. Say again? That is the phase velocity of the wave, so well remembered on that. You get a brownie point. Joe, you were in the group also. What's the wave?
Omega is CK.
Yeah, omega equals CK. So that, really, that equation, that straight line equation is V equals F lambda. So, what we're going to do now is to say, rather than a single slab of glass, let's change it and turn it into the same sort of spatial size of system, but I'm going to make one layer, one material, another layer, another material, red, yellow, those are different materials. Maybe one is zinc sulfide, another is magnesium fluoride, those are the typical samples that we use, and we choose those two different materials because they have a different set of refractive indices. Now, what we have introduced is analogous to, instead of an atom here and an atom there in electron systems, in condensed matter systems, if I'm going to put a lot of these atoms here, well, electrons can just hop from one atom to another if they're not connected in an ordered way. If we have a crystal of atoms, then as I send an electron through this crystal of atoms here, all of which are regularly spaced with respect to each other, that electron will see valence bands, conduction bands. In other words, it will see a series of bands. And those bands will affect the way the electron propagates through this crystal system, be it a metal, be it a dielectric. What we find is that when we do the analogous thing and we place a spatial ordering on this physical system, that affects the way photons propagate through this system. And this is the way that it affects it. Rather than every single frequency being related to a given wave vector, we have some frequencies that just don't have wave vectors. There's a gap in the omega with respect to k relation that prevents the propagation of these frequencies. In other words, of these wavelengths. In other words, of these colors. So what we're looking at there is a gap in the way photons can propagate. The absence of a solution, I suppose. And in the absence of a solution, these photons can't propagate, and if they can't propagate, what do? Who can tell me that?
Flat.
Yeah, absolutely right. Unless, that was a good answer, I'm going to push you further, which is what I do. They will reflect unless, what else might go on? We've got transmission, we've got reflection, what else have we absorbed? That could be absorbed if the materials themselves are absorbing. So we've covered quite an important and quite a profound aspect of photonics. Now let's get away from the background, let's get into the fun stuff. Let's talk about crystals. Here's some schematics. We can introduce that order there either in 1D or 2D or 3D. And biological systems specialize in doing all three. Not with straight edges as we've illustrated here, but with a very energy minimal type of approach. So, top level, we talk about photonics, we talk about band gaps. That's a little bit jargony, hard to access. Let's simplify it down a bit. Eros earlier showed a beautiful picture of a soap bubble, and he described wave interference as the mechanism producing the colors in a soap film. Here's some wave interference. Light comes down at a particular angle, we get reflection from each interface. With an appropriate thickness, with an appropriate, let's give it a label, this periodicity, this spacing between interfaces. If they are regular, and if the angle is right, and the refractive indices, A and B, are appropriate, we will get strong constructive interference in reflection for one wavelength, strong constructive interference in transmission for another wavelength. And it gives rise to very strong color effects. Some of you will have seen this video in excess of 10 times already, but it doesn't reduce the impact it has. So what color? Here's my question. What color is the color? What color is the color? There we go. Okay, it gets me every time. The color of the car is not fixed. It varies with angle, and that gives rise to the definition of the word iridescent. It's an iridescent color. which is only accessible through this idea of photonics, the idea of wave interference. We just think it's going to be different when it goes away. Well, it never is. So, let's get into the meat of the biology now, some of these biological systems. We have nanostructure in morpho, and I'm going to zip through this as the butterfly comes in and goes out. We looked at this very early on, about 15 years ago, and we found that it was the structure within the scales that comprised the high degree of spatial order which produced this interference. The coherent scattering, that's another phrase for it. As we look down on that, we're looking down on this. So these are the tops that we see just here. And it's those layers, in fact, it's the thickness of these layers and their refractive index and the gaps between them that have evolved perfectly to give a bright blue reflection. If we were to change these layers, thicknesses, or their material, then we would affect the color reflected. These are, I mean, some of you might have seen me do this in a lecture or otherwise, but what happens if I drop a bit of water on here? What would happen? Isabel? Hydrophobic, because you're in the third year lab and you know about this stuff. Well done, yeah. So why would water form a droplet on top of that?
Because of the spiky nature of the material. It basically interacts with the water surface tension and sort of props it up in a sense.
100% right. Excellent, okay. When water droplets, rain droplets, or dew forms on the top here, it doesn't penetrate. In other words, we still have a material air set of periodic surfaces. But if instead of using water, which is a high surface tension, we put a bit of alcohol on there, and I'm not talking about the sort of alcohol you will be drinking in about 15 minutes, some of you, but pure alcohol, ethanol, let's say. If I put a bit of ethanol on there, that immediately gets sucked into all these gaps, and it changes the refractive index contrast, thereby changing the color reflected from a bright blue to a wonderful, equally bright green. And if you haven't seen that, please stop by the lab and I'll happily treat you to an alcohol demonstration. That sounds wrong, doesn't it? You should edit that out. But you understand what I mean. So these types of structural color effects have been used in industry, not least by this L'Oreal stuff that we were lucky enough to work with a little bit. They marketed the colors here on this eye-related makeup under their Lancôme brand, and it was a Lucy was the name given to it. One might wonder, are they crushing up? That was the first thing that the journalist asked. Are you really crushing up these beautiful creatures? No, we weren't. So the sort of things that go into the material are flakes, tiny little flakes that I have again up in the lab, and they're really, really nice. It just looks like dust on your finger. I'm going to dip it into this sort of packet, put it on here, and yeah, it just looks like a red, in this case, dust. But as we zoom in, you start to see that these flakes have slightly different colors depending on their angle. Some of these are tilted with respect to others. And the size of them makes them amenable to being embedded in a transparent medium, a liquid medium, a viscous medium which you can then put on your lips or your eyes or wherever you are. Now, that's all very well, and that's a very simple multi-layer system, very flat. Here is a slightly different synthetic system. Looks a bit broadband, but this has a special twist to it. And as we zoom in, you might start to see the twist. You can probably see it just there. Well, these appear to have lines. Why might we see, again, at this type of magnification, why might we see lines? What could they be made of? Or what could their physical structure be if we're seeing lines? Well, we wouldn't necessarily see, the other ones were material layers on top of the other. We're looking down on them. Oh, it could be, yes, you're right, could be. In this case, it's not. It's even more simple than that. This is, does anyone on their shed at home or otherwise have a corrugated steel, corrugated iron? That's what these are. If you take one of those big corrugated steel sheets and you miniaturize it down to this scale, this is the effect we would see. So these colors arise due to diffraction rather than interference. And those two aspects are related. They're both coherent scattering. One is with a periodicity in that direction. The other with a periodicity, let's say, across the surface in that direction. And we can see the difference. That is an old style flake, flat. These are diffraction grating. When we illuminate, not from above, which is referred to as bright field illumination, when we illuminate, here's the sample. Instead of from above, which is that picture, I'm going to illuminate from the side and collect light scattered straight up. That's referred to as dark field illumination. Look what happens. So not only does that disappear, because now we're not collecting at the mirror angle, but here we're seeing different colors because we're collecting a different diffracted order. So let's get on to the disorder, or approach disorder. Here's some wrinkles. That's one of my young children when they were born, or just after bath time when they were born. Here apparently are the dogs we're getting for Christmas this year. Here's the person who requested those dogs. And here's tends to be what happens between myself and my wife before we go out on that rare occasion. Let me be a bit more serious now. So we studied this is a dragonfly, and it's a beautiful piece, really, really nice. It's Rhyothamus. The colour here, you can see just by looking at the surface that it's a structural colour. And we give it that title, structure, because it's not a pigment-based colour. This is black here, this is transparent. So this has no pigment whatsoever. That has a lot of melanin. This has some melanin and a lot of periodic structure. Let's have a look at that periodic structure. This is the surface. I'll bring your attention to this 2-micron scale bar. This is very small. This is an electron microscope image of the surface. Here is another electron microscope image, but this time of a cross-section through this surface. So all of these wrinkles here correspond roughly to the wrinkles there. Not, this isn't that sample, but it's an analogous sample. Look at the layers. So we have layers going down in, and those layers produce the structural colour. But we asked this question. You can see this in 1,000 different damselflies and dragonflies. Our question, and this is quite a high-level question, is what's the effect of the wrinkling? So if I choose to go out of an evening with my lovely wife and I forget to iron my wrinkled shirt, what's the effect apart from marital disharmony, or however you want to call it? Well, let's examine the effect. Wrinkling is a form of disorder, or quasi-order, however you want to label it. What we're going to do, first of all, is do another measurement. Let's try to quantify over quite a large area the level of the wrinkling. Because that wrinkling is very different to other species. It's relatively unique to a small group of species. So what I'm going to do is use atomic force microscopy. And if you're not familiar with what that is, I'm going to use my arm as some big cantilever that I can control, and I know if it's going up or going down because either I reflect light from it, and that light reflection moves compared whether it's here or whether it's there, or there's some sort of piezoelectric control, and I know whether it's going to be pushed up or pulled down. On the end of this cantilever, I'm going to put a very sharp object, and I'm going to look at my surface, and I'm going to scan this object across the surface. I'm going to get to there, jump back, move down a bit, get to there. Oh, I found something. So now, as I move it across this surface, it's just deflected this arm a little bit. Go back to there, move down a bit. So what I can do by rastering this tip, this very sharp tip, across my surface, I can record the deflection and use that to build up a surface profile map, a map of the features, a bird's eye view of moving across the surface, really. It doesn't get subsurface, and it doesn't get into cracks that are right inside caves, as it were. But we can build up this, and this is an AFM map of the damselfly wing surface, a small region, 0 to 50, 50 microns by 50 microns. So everything that's black, here, is at that particular height. Everything that's sort of white and yellow is at that height. So there's about a micron of difference in size between there and there. And we can do it for various surfaces, and then pull out line profiles. And here is a line profile that we pulled out from right thinness. The black line is the actual real data. Every surface has some lower level noise, and these models here are that. But the blue line is the interpolated, smoothed curve that represents the true nature of the wrinkling. Now, we have no benchmark. I can tell you that this is a really wrinkled surface, but you can say, sure, yeah, but how do I know it's wrinkled? How do I know it's not super wrinkled or just relatively flat for a biological surface? Well, let's compare it to a typical damselfly. A typical damselfly compared to Rhythonis is this. That's Matronodes. That looks like that. So they have the same scale as these axes, but you can see that's not completely flat, but now you can see the relative difference. It's not massive, it's not 10 orders of magnitude, but it is enough to what we think create a significant difference. And let's look at that very briefly. Optically, what is the difference? Now, this is quite a tricky thing to interpret. Here's what I'm going to do. I'm going to put a sample down on my surface. Where'd that pen go? And I'm going to shine light in at this angle. Now, if that surface is tilted like this, or if it's tilted like that or like that, then the reflection will go there, or will go there, or will go there. If this is all crumpled up like that, and I hit it with a really big beam spot, where's the reflection going to go? Well, it could go anywhere. It could go anywhere in this hemisphere, right? So I'm going to pick this hemisphere up, and I'm going to flatten it. The edge of the hemisphere becomes a circle, and that circle lies right on the edge. The bit of the hemisphere that points straight up is just there. That's 5 degrees around the center point. And that's 30 degrees, and that's 60 degrees. So what we are seeing is this blue reflection from Rhythonis spread out over quite a significant part of that hemisphere. Now, again, that means nothing unless you see it compared to something else. So let's compare that. If that was a reflection from here. Let's compare the same like-for-like measurement as a reflection from there. And then this is what we see. So the reflection from that less wrinkled surface is really narrow. So I'm going to ask you this. What advantage or what cost to each insect is that appearance compared to that appearance?
You see it in much greater angles.
Yeah, there you go. You've hit the nail right on the head. So the introduction in this species of a reasonable bit of wrinkling on its surface gives rise to a better conspicuousness. If that's of benefit, then it will evolve it in, let's say. But it can be a cost. Under what conditions is it a cost?
You're going to lose intensity.
You're going to lose...
If you go straight down, it's going to be way more intense.
You're absolutely right. So in terms of functionality, well, no, intensity is a proper physical answer. What I was after more is, what about predation? Which one's going to be predated on more or less? Well, possibly that one will be a bit safer compared to that one. If that one's more visible to what we say are conspecifics, the same species, then it's going to be more visible to its predators as well. There's a cost and a benefit associated with that. And I suppose, and the Darwinian argument is, if the benefit outweighs the cost, then that's a trait, that's a phenotype which will stay, which will remain. So, photonic bacteria, and I know I'm kind of running close to the deadline. I'll try to be just a few more minutes, and I might accelerate a little bit. Here's a sea anemone. We're really getting onto the nature of biological noise as I want to talk about. That wrinkling was a certain level of biological noise in one sense. We worked with a group in France, and one of their postdocs came over and stayed with us, and Peter very kindly let her use the prep facilities in his lab. And she was able to isolate some bacteria from that sea anemone. And this bacteria was called cellulophagia. And here is a bit of a sort of bacterial growth of this bacteria. And you'll notice that many bacteria are yellow. Anyone have a dodgy tongue at the moment? You know, sort of white, furry, that's what people call it. Well, I'm not sure if that's bacteria, but that's the sort of picture I have in my head of bacteria. When I open my old tin of beans, you know, that's in the back of the fridge, You know, I look there, it's a bit green. No, that green is often indicative of a pigment-based colour. It's not this type of colour. Bacterial pigment colour is very common, but what's less common is structural colour in bacteria. Now, a damselfly or a butterfly flying beautifully here is an example of a great example of colour within a single species. What we have here is colour created by a population rather than from within a single species. So in one sense, it's a very different type of appearance generation. This is a cross-section through a bacterial film. In fact, this is a cross-section through a bacterial film that is not structurally coloured. Remember what we're looking for really? We're looking for order, regularity. And although you can sort of say, yeah, they're kind of ordered together, they're not really, are they? Compared to some of the images we saw earlier. Let me now show you, in contrast to this, a picture of a cross-section through a structurally coloured bacterial film. And there it is. Now, on the one hand, I could say, wow, that is a significant difference there. Look how ordered it is. And I'm going to say that. Look how ordered it is. But at the same time, in the next breath, I'm going to say, and yet. Someone finish that sentence off for me. And yet what?
Disordered.
Yeah. Now, would you say disordered? Is that the right word? Is? I'm glad you're sort of furrowing your eyebrows there, because that's exactly what I'm doing in my head. Disordered. I'm looking at that thinking, is it disordered? No, it's not really. Is it perfectly ordered? Definitely not. So it sits somewhere in between. What this system has done, and this is very loose terms, it has made a perfect system. It didn't actually make it, but let's start in our minds with a perfectly ordered system. And it's taken one of those scattering elements and it's moved it a bit. And another one moved. In fact, all of the positions of those bacterial samples, it has just shifted a little bit. It has applied a bit of noise to it. What we're seeing there, what you described initially as disorder, is noise, structural positional noise. Hence this title of the talk, biological noise. Now I'm going to zip through this very quickly. We can change the colour. We have a little bit of leeway playing with the colour. We can change growth medium or the strain, the concentration, or even the age, and that will affect the colour that is produced by this bacterial self-organisation. But now let's get on to a bit more fundamental physics. I'm going to do 2 more minutes and then stop. Here are some TEMs of disordered bacterial films. Bacterial films that are like this or like that are not structurally coloured. And what do we notice? Well, we notice they're not very ordered. How do we know? How do we quantify that? Well, you put a grid down. There's the grid, 2 grids. And then you use in ImageJ or some software, you use the information that applying the grid provides you. In other words, it will tell you how big the centres are and how far apart they are if you use the right recognition software. And when we plot the distribution of distances between nearest neighbours, that's what we see. So here's the distance, this is the number. So around here is a sort of, well, kind of the mean distance between nearest neighbours is 500 nanometers. What I'm going to tell you right now is that these are very, very wide. What would it look like if it was perfectly ordered? Yeah, it would be a really tight curve, a tight distribution, a delta function almost. Now, that's a disordered system, or quasi-ordered system. Now, these 3 are more ordered systems. Let's throw the grid at them. This is a Voronoi analysis, if you're interested. And now let's plot the distributions. These are much more tight. And even though they're not disordered, they're not really wide, they're not perfectly ordered either, are they? Because they have a width. What we're going to call that is a full width half maximum, let's say. I'm going to say that this actually right here is of the order of 100 nanometers. Now, imagine we're going to look at things like this. From a 2D worm, from a peacock feather, from this bacteria, and let's do the analysis on different biological samples. And let's say, okay, this analysis we're going to apply to all of these for these three animals, look at the sort of distribution we get. In other words, this is where we're going with this, right? We want to say, synthetically, up in the lab, if I want to make a perfect photonic crystal, I've got to spend a lot of money on the fib, some sort of process that is very painstaking, and when I make this photonic crystal synthetically, it's only going to be really small and pricey. But it will be great. The performance of this really small, really expensive sample will be brilliant. These guys perform, they serve their functional purpose remarkably. And yet they put up with imperfection. That's the message we want to hone right down on. How do we make use of that? If we want to make use of it, we have to understand it. So, let's try to do a bit of modeling. I'm going to zip through this. If you're interested, we can talk about it later. Here is a model. It's a computer model, a 2D photonic crystal, square symmetry. And that's how perfectly ordered it is. That full width half maximum is 0. Let's throw a bit of noise at it. That's that particular full width half maximum. Let's throw more noise at it. There it is, a bigger full width half maximum. And then we can put that into our optical, our electromagnetics package, and see what the performance is. Theoretically, right? Because this is a theoretical project. And this bit of a convoluted, badly labeled diagram is what we get for part of the model. As we start from ordered, well, at the order we get a very high intensity, and we get very little spread. So that's the scattered angle, how wide it's scattered. As we increase the disorder, the intensity comes down, but the angle of scattering increases. And that's a valuable lesson. Here is a CIE chart. That is what color scientists use to understand the appearance of objects in relation to their color components. Let's zoom into this region. As we increase the disorder, we move towards this central spot, and that central spot is called the white spot, where all the colors are blended with equal intensities and produce this appearance of whiteness. Perfect disorder makes white. Perfect order gives us, well, let's project this back, a saturated color. If your object, like this laser, if we measure how pure it is, then if it's a very pure color, it will be sitting right on the edge somewhere. Around here. So, I think I prefer to go from this. Well, actually, no, let me finish. I'm going to skip over the white beetle because I've taken up far too much of your valuable social time. Let me show you this, and then we'll go to the title slide. I may have to skip something. Here's a very interesting weevil, and that has some scales in this particular region that are very ordered in a three-dimensional sense. In another region, we have scales that show what looks like disorder, but when you do the analysis, it's actually halfway between. It's a quasi-order. That's the reasonable phrase to use. Now let's look at the cost and the benefit. Let's go back to our scattering hemisphere. I'm going to put my sample down, one of these weevil scales down. I'm going to shine light straight from above, white light, and see where it scatters. Here's the hemisphere. It's a big sort of semi-sphere. I'm going to pick it up and then flatten it. That's the response from the perfectly ordered system. A little bit of spread, but a pure color. But when we do it for this system, what do you expect? Tell me that. Much widely scattered angle, and well, it's not as pure a color. So this is, again, a cost or a benefit, depending on your perspective. So, some of what I've shown you has been about noise. You've all become quite quiet, which suggests the day has been a long one. And I should have finished 5 minutes ago. Let's zip past Gandalf and get on to this summary here to say, right at the end, the key message from this talk is really the essence of the most recent part of my team's work. This idea of noise, positional, photonic noise. It's not the acoustic noise that we normally associate, but it's the idea, the fact that biosystems can tolerate this type of positional, structural noise and still deliver a great photonic performance. So, on that note, on this biological noise note, see if you can spot my daughter there. It's been a great pleasure to talk to you this evening, and thank you for your attention.